Even the greatest scientists in history can find themselves on the wrong side of some theories. When new physics emerges that challenges the current paradigm, it can often send ripples of skepticism and uncertainty through the scientific community. In the early 20th century, with the emergence of the quantum world, one of the most famous scientists of the day, Albert Einstein, had some issues with what was revealed. The start of the quantum revolution began in 1900 when Max Planck put forward his theory that energy existed in individual units, or quanta, instead of a constant wave of energy as was the understanding of it at the time. Over 2 decades later, in the 1920s, scientists from around the world would collaborate to develop the first attempt at a full theory of quantum mechanics. What they uncovered was an entire subatomic world that seemed to ignore many of the laws of physics used to describe our world, and whose randomness goes against the straightforward logic tied to conventional physics. One famous aspect of quantum mechanics, uncertainty, was built into the framework as the Heisenberg uncertainty principle, introduced by Werner Heisenberg, which helps to define what properties can be known about a particle. We cannot know both the position and speed of a particle at the same time with perfect accuracy. As the accuracy of one measurement increases, the uncertainty of the other measurement increases as well. Today, these uncertainties and other seemingly random quantum events are much more understood and are built into the theories that have been rigorously tested over the last century. But during the early years of quantum theory, there was a relatively large group of physicists who were not happy with the explanations that were being put forth. The largest of these voices belonged to Einstein, who believed that the universe could not be governed by laws that rely on randomness, famously exclaiming, "God does not play dice with the universe." To which one of the fathers of quantum mechanics, Niels Bohr, quickly replied, "Einstein, stop telling God what to do." But in the years in between Planck and the development of the first mathematical framework describing the quantum world by Bohr, Heisenberg, Schrödinger, and others, there were a number of discoveries that aided in the development of this theory, even from Einstein himself. It's a common misconception that Einstein won his Nobel Prize for his theories of special and general relativity. But his only Nobel Prize was actually for his work on the photoelectric effect in 1905. He was able to explain how electrically charged particles are released from material when it absorbs electromagnetic radiation. Basically, if you shine a light of a certain frequency onto a piece of metal, the photons in that beam of light will knock off electrons from the metal atoms. This discovery came just half a decade after Planck first introduced his idea of quantum packets of energy, and helped strengthen that argument by proving that energy in light is composed of individual particles called photons. But even if his work helped further the theory of quantum mechanics, he still had a hard time accepting many of the ideas that started coming forward. Einstein's main concern when it came to the theory of quantum mechanics that was being developed was based around how indeterministic it was. Prior to this era of physics, theories and laws were based on certainty and determinism. In order for a theory to be accepted, it had to demonstrate that it could predict events with perfect accuracy based on what could be measured. But now, physicists were expected to accept a theory that, at its core, was built off of a variety of uncertain subatomic events. One of the first features of quantum mechanics to face objection was the idea of quantum superposition, that a particle can be in multiple different states at the same time, existing more as a wave of probabilities than as a physical particle. The quantum wave function was introduced by Erwin Schrödinger in 1926 as a way to represent the possible states of a particle at a given point in space and time. This equation deals with the probabilities that particles will be in specific states and can be used to determine the chance that a particle will end up in a distinct state. But as soon as that particle is measured to determine the state it's in, the wave function collapses, the particle ceases to be a wave, and it ends up in a single state. This concept can be hard to wrap your head around, as it doesn't really sound like reality would behave this way, which is exactly what Einstein thought. To try and understand this feature better, take Schrödinger's famous paradox to explain the superposition of quantum states. Inside a box, there's a cat and a radioactive material that has a 50-50 probability of decaying, which would cause the cat to die, or not decaying, which would mean the cat is still alive. While the box is closed, you could argue that the cat is both alive and dead at the same time, as both have the same likelihood of being true. So the cat remains in the superposition of being alive and dead at the same time until someone opens the box. Opening the box changes this system in a way which forces the cat to be in one state or the other, instead of existing in both simultaneously. Well, not too difficult to understand. Accepting this as the way the universe works on a fundamental level was difficult for some, and Einstein, along with two other physicists, Podolsky and Rosen, attempted to find a way to disprove this. They proposed the following thought experiment. If two quantum particles become linked together in a way that can be measured, and then separated by a large distance, if the property of one particle was then measured, the second particle would have to respond instantly. This thought experiment was implying that either quantum information can move faster than light, or that the states of the two particles were fixed, and the two weren't in a superposition of states until they were measured. They were convinced that there was some variable hidden from the current view on quantum mechanics, and this missing piece, the so-called hidden variable, would help to eliminate the uncertainty and randomness. But in a cruel twist of fate, Einstein once again unwittingly helped further the understanding of quantum mechanics. His thought experiment was the first to describe another piece of quantum weirdness that we now call entanglement. This feature of quantum mechanics means that two entangled particles can affect each other across any distance in an instant. And yes, that means faster than light speed, and was experimentally proven in the early 1970s by physicists John Causer and Stuart Friedman. And to this day, quantum superposition has been proven by a number of different experiments that have proven this to be a feature of the quantum world, and the various quantum theories are among the most accurate theories we have to explain the universe. But even to this day, there's still some scientists that continue to believe what Einstein once did, that something must be missing within this explanation, a missing feature of quantum mechanics that would take away the randomness and uncertainty from the framework, some type of hidden variable. While Einstein didn't like some of the features of quantum mechanics, he didn't dismiss the whole theory. He simply thought there was something missing. And to this day, there are physicists working to try and uncover these local hidden variables that would allow them to make quantum mechanics more deterministic, in which case they could predict events with accuracy. But even with all the randomness and uncertainty included in the current theory of the subatomic world, physicists have been able to achieve amazing things using the concepts that Einstein hated. The quantum computers in development that can perform operations millions of times faster than current computers achieve this by utilizing quantum superposition to create something called quantum bits or qubits that can be in many different states at once to replace the classic binary bit that can only be in one of two, the 0 and 1 that we're all familiar with. And quantum entanglement has been used to develop the emerging technology of quantum teleportation, in which information can be sent instantly across vast distances. The mathematical framework that's been developed to explain quantum mechanics is extremely accurate and well tested. So even if there are hidden variables that will remove some of the weirdness of quantum mechanics, they would most likely fit into the current theory smoothly and add to our understanding of the universe. Thanks for watching. Do you think Einstein's instincts were right and that there's something missing from quantum mechanics? Or do you believe that this randomness is built into the foundations of the universe? Let us know in the comments below. See you next time on Matter.